How many of you are using syntax trees for anything, building anything interesting in your apps? That guy.
Does writing code count?
Oh, yep. Okay, so we've got 2 people, awesome. So this talk is for everybody else to try and get you pumped up and see maybe what you're missing or what else there is to learn about syntax trees to help you build more exciting and interesting apps. The first thing that I'm going to do is talk about a little bit just about how you get started with syntax trees, and then I'll talk about some of the amazing things that you can build with them and how they sort of help you think about your JavaScript maybe at a little bit of a higher level than you used to think about them before. Sort of giving you tools to build JavaScript so you don't actually have to build it yourself. It's pretty amazing. First, I'm going to talk about parsers. Now, a parser is something that will take your code and convert it into something called a syntax tree. So you shove in your code, and out on the other side is a tree. It's like a reverse like mulcher. You know those things when they cut down the tree, you shove in the tree trunks, and then you get like some sawdust. The sawdust is your code. You put it back in the machine, and you get the tree on the other side. It's pretty exciting. So you have some code like this, console.log UtahJS, and then you shove it through the parser, and you get your tree. Now, if you look at this tree, it has these different little blocks. They're called nodes. Nodes are different parts of the tree. They describe what's happening in your JavaScript program. Now, this is a very, very small program, so there's only just a few nodes. But if you start to look at them, call expression, member expression, expression statement, these types of nodes, this same pattern will be in any program that you're having out there, anything that you're building. And the cool thing is once it turns into a tree is actually represented not as a picture, but as a JavaScript object. I know it's very difficult to read, don't worry about it, because you know what they say, like a picture speaks 1,000 JSONs or something. So you should just be able, we'll just use pictures because it's a lot nicer than the tree form. But just know that anytime you see something like this in my presentation, it really just represents a JavaScript object. And each of these things can easily be manipulated or inspected using the standard JavaScript tools that we're all used to. Now, let's talk about what parsers are out there. So there are a bunch of parsers out there that people use. There's Acorn parser. It powers things like Babel. So you know it's pretty good. There's the Esprima parser. Esprima really started this JavaScript parsing in JavaScript revolution. So it was made by the guy who made Phantom.js, which is a really cool project, super smart guy, Arya Hidyat. And he came up with this Esprima parser a couple years ago, and it's been the foundation of really a shift in how we build tools in JavaScript. There's another tool that I really like called ESTree. It's what we use in ESLint. It's kind of a fork of Esprima. We worked really hard to get a bunch of ES6 features into it really early on so that we could lint all your ES6 code in a super nice way. So those are the different tools. For the most part, all their APIs are basically the same. If you want to parse some code, if you want to generate one of those trees, you'll just say espree.parse or esprima.parse, acorn.parse, whatever it may be. And then they also take options. So you can say, hey, I want to parse ECMAScript version 6 code. This is the Acorn API. You pass in ECMA version 6. I don't know what they're going to do about the 2015 and the 7 and all the different versions, but whatever. That's a silly thing to worry about. So what you need to know about ASTs, though, now that you know the basics, there are parsers, they take your code, they turn it into trees, is that these ASTs are everywhere. You can use all the cool tools that we're using today, things like Babel, things like Istanbul to do code coverage, all the fancy things, all the fancy magic, CoffeeScript, whatever other fancy stuff is out there, it's secretly using ASTs. And I want to show you how you can use these same tools to build amazing things that you didn't even know that you could build. But you can, because you're amazing. Thanks, James. So some of the things that I really like, and then I'm going to show you how to build with ASTs, are build time code transformation tools. So this is things like Babel, right? At build time, you convert your code from one thing to another, or a minifier fits that example. The next thing will be one-off code migration. So say you're upgrading your application architecture from one version of a framework to another. You can build tools to help you with that migration process. And then code inspection. How to write custom rules for things like ESLint to really understand what's happening in your code and slap you if you're doing the wrong thing. So we will go through this quickly because you're all very smart, and I know you can follow along. So for code transformation, how many of you use Babel? Okay, about a third of the folks here. Just curious, how many of you are using React as well? Okay, yeah, I know a lot of React people are using Babel, but there are obviously other use cases as well. I really enjoy using ES6 features. Babel is great. But Babel also lets you create plugins. And there's this great example on their website of creating a custom plugin. I really like this example. I'm going to read it because it's funny. It says, Bob hates function declarations with a passion. Nobody knows why. Bob loves to enforce this on his coworkers. He snuck this plugin into their build system to force his tyrannical code style. It's so devious, you know? Who knew that trees could be so evil? So what we're going to do is look at how they build this. The first thing you'll notice if you look at the files there is that there are 3 files and only one of them has code in it. So you're thinking, hey, I can probably do that. That's just one file. And the second thing that you'll notice is that it's like 10 lines of code. I've separated out one of the pieces into a function. But if you want to create a Babel plugin, so if you want to transform something at build time, something interesting, think about what those things might be. You'll export a function. This is all node style, common JS syntax. But you'll export a function that returns a new Babel plugin instance with a name. And then you kind of have this funny object that you pass for your options. This object has something called a property called visitor. And when you're working with ASTs, these syntax trees, you'll notice this pattern all the time, this visitor pattern, where you pass in an object to one of these tools and you'll say, hey, I only care about, you're going to go through the whole tree, but I only care about nodes that are of this type. It's kind of like, in a way, sort of like, you know, like jQuery style, if you want to match a certain selector. This is kind of the way that that happens in AST land. You'll say, I only care about function declarations. So anytime that I'm going through that tree, I'm looking down at all those nodes, if I see a function declaration, then I'm going to call this function on the right-hand side. So let's see how hard it will be to write this Babel plugin that converts function declarations to function expressions. So first thing that we're going to do in this function is grab a hold of the ID. The ID is like the name of the function. So we're going to keep the name of that function. It's an object that can tell you about the name of the function. The second thing that we'll do is we'll change the node type. So it was a function declaration. We knew that because we're only visiting function declarations. And we're going to say, let's make this a function expression. I see a few faces out there being like, what is he talking about? Just bear with me. It's going to make sense, I promise. And then we're gonna null out the ID because we're going from a function declaration, which has that name on it, to an expression, which we're going to name a variable and assign it an anonymous function. Think about what's happening here. And then finally, Babel has this cool API where we can say, we want to return a new variable declaration, and the thing that we're declaring is going to be this name that we give it, and then the node is now this new function expression node. Let it sink in. I'll show you what it looks like. So you've got your function help. With that little plugin, about 10 lines of code, you can transform that at build time to something like this, var help equals function. Now, this is not very cool, but you can build cool things using this simple technology. So think about in your code base if there's something you'd like to change. For example, I think one really interesting case for performance might be, let's convert all of our for each statements or map statements to for loops. That could enhance your performance. Those types of things could be something that you'd use at build time. You don't necessarily want to code that way, but these build time plugins can help you optimize your code before production. Next, code migration. So that sort of stuff is good for those one-off transformations or those build time transformations. But there's this migration step a lot of times. Let's say you're moving from like one version of React to the next, and even though it's like 0. version, there's like 20 breaking changes or whatever. I don't know. That's just how they roll. So, or you want to move from like function prototypes to ES6 classes, or vice versa. Maybe you hate classes, you want to go the other direction. One-off code migration might be the right step. Now, Facebook recently released this really cool tool called JS Code Shift. It's built upon a whole bunch of other technologies, but it's a really super simple, chainable API that lets you write these little scripts that you can use to convert your code base from one thing to another. It's really neat. I think it's really, really nice that they came out with this just like a couple weeks ago for my talk. I'm really grateful for them. Any Facebook people here? Okay, fine. I won't be thanking them. So here's what that API looks like. Again, you export a function that takes some information in. Here, this function is actually going to return source code. So you pass in the current source code of the file that you're working with. This particular example is going to take all variable declarators named foo. So anytime you have var foo equals something, Then it's going to let you rename it to bar. I think that's nice. I mean, it's really simple. It helps you see just in 3 or 4 lines of code, then it converts it to source. How you can build something very, very simple, but potentially very powerful. React uses this exact same tool for all their, the React team uses this tool for their code mods that they release. So when they come up with a new version of React, they have this code mod that lets you automatically migrate to the new version. Anyone use that tool? Awesome. Great. Thanks. Come on, audience. You need to work with me here. What about Angular? Any Angular people? Okay, I don't know anything about Angular, but I'm so glad that you could make it here. I'll try and get you excited about this other stuff instead. So the last thing that hopefully everyone can be excited about is code inspection. How many of you use like ESLint? Yeah, thanks so much. And JSHint people? Yeah, it's a great tool. There are so many great tools for linting your code. The genius behind ESLint is that when it came out, what I think Nicholas Zakis realized is that the problem with the previous generation of linters, including JSLint and JSHint, was that it was really, really difficult to add new rules into the process. Did anyone ever try the awesome process of trying to add a custom rule to JSLint or JSHint? How did that go for you?
Not nearly as cool as ESLint.
Okay, thanks. That was a great, yes, I am awesome. No, just kidding. No, I didn't make ESLint, but I do really like contributing to it. I think it's a fantastic tool. The problem that JSHint had is that it has this parser. So the code is this like several thousand line parser that goes through, that understands your code, it parses your tree, and then inside the parser, inside that huge file, it's at least this big, at various points within the file, it will apply rules. So if you're going through and you're parsing, say, function parameters, and it'll go and then in that block where it's parsing the function parameters and trying to understand them, it's also counting them. And then it might flag the rule that says you have too many function parameters. Well, unfortunately, it's really, really hard to understand and maintain code that is all bundled together like that. So what ESLint did is it separated the rules engine from the parsing. So first it will take your code, convert it into a nice tree, and then we'll pass that tree into all these rule files. And the rules themselves can inspect that tree and look for potential violations of the rules. So every rule is very simple. If you want to add a custom rule that says you don't like any variables that starts with the letter W, you can do it really fast. It will be very easy to do. Here's a rule that I'm going to make for fun and to be silly. So here's an example of writing a custom rule with ESLint. You export a function that takes this context thing. The context thing is sort of information that ESLint provides. And then you're going to return an object. Now, this uses that same visitor pattern that I talked about before. It's just an object that says what nodes you care about in the tree. You might care about function expressions. You might care about function declarations. There are a whole bunch of different node types. We'll talk about what some of them are in a minute. But here we're just going to look at class declarations. And it's going to go through that tree and say, anytime I stumble on a class declaration, let's just report that your code has no class. I thought that was funny. We could have any sort of rule here that we wanted, but this is a very simple example of how easy it is to write rules for ESLint as soon as you start to understand the different nodes in the tree. Now, understanding what those nodes are is kind of complicated because there's so many different types of nodes in that tree. You know, when you have trees in nature, you might have an apple tree or a plum tree or a cherry tree. They're different trees. But unfortunately, syntax trees, like their fruits, those little nodes, come in many, many varieties. And it's really complicated. Imagine if you had a fruit tree in your backyard and it had 100 different kind of fruits. You'd go out there, you never know what you're eating. It would be very hard to make pie. It would just be a really sad time. With JavaScript syntax trees, though, there's this spec that has been created recently. Basically, as all these different parsers were coming out and all these new language features started happening, they decided, the different parser authors decided that it might be nice to start standardizing what these new features, like these new ES6 features, for example, would look like when put into a syntax tree. And so these folks came together and created this ESTree spec, kind of based on some work previously done by Mozilla called the SpiderMonkey API. But this is really nice. It's on GitHub. It's really easy to see. If you find an issue in the tree, like the tree has something that doesn't make sense, you can just file an issue here. And they're very responsive to try and make sure that all the different parsers speak the same tree language. I don't know. They talk about the same things. So now that I've given you this sort of broad overview of what's possible with these parsers and what's possible with syntax trees, I wanted to really take this idea to heart. The AST gives you superpowers. It lets you abstract away your thinking from looking at actual individual lines of code to looking at and building tools that let you manipulate and inspect your code. It takes you to this level of like, sort of robots writing the code for you, which is kind of neat. So it also reminded me of this quote from this book called Learning Perl. Anyone know Perl out there? Anyone read this book, like in the old days? I read this in middle school, and it really got me excited about programming. You're awesome, you're awesome. All of you people are awesome, by the way. It has this great quote at the top. It says about Perl, making easy things easy and hard things possible. I think in JavaScript, trees make hard things possible. Learning and understanding syntax trees will give you the power to do things that you probably thought were impossible. So they're well worth learning, and what I want to show you for the next 10 minutes or so is an example of building something that sounds totally crazy using trees. So we're going to take a stab at building a JavaScript-aware version of Git diff. So how many of you use Git? Okay, cool. That's a lot of people. I don't know why I asked that. It's kind of obvious everyone uses Git today. But you might have kind of stumbled on this issue that I'm going to share now. So say I have some code like this, and then let's say, hey, you know what, I'm going to re-give this talk somewhere else, so I'm just going to change it a little bit. And now, but I'm still here, so I need to make that an error because other confs are bad or whatever. So if I put that into Git diff, I get this fantastic output. It basically says, your first line is gone, replaced with this new line. Now, that sounds okay, and with a small program, you might say, yeah, that's probably fair. But if you look at it carefully, if you actually know JavaScript, you're like, wait a second, console. Console is the same. Wow, that's the most important thing. What object am I calling something on? I'm calling it on console. And I'm calling a method on console, and I'm passing it a string, and that's the same. And so there's a lot of the structure of the code that's actually exactly the same. It's kind of rude, I think, of Git to be so dismissive of the previous code when clearly we're just building off of that previous greatness. So I will show you how we will try to build something more interesting using our knowledge of syntax trees, which we've gained in the last 10 minutes. So anyone use this command, git diff -- raw? Some really cool people. I just discovered this like a while ago. It's pretty interesting. It lets you look at sort of more internally what diff knows about the changes. And so if we were going to build a better diff, what we really need to know is what files changed and what did they look like before the change and what did they look like after the change. And we can get that with this command git diff -- raw. If you look carefully, you'll see it has a bunch of stuff. File permissions, MD5 hash. Okay, MD5 hash of the previous version, we can use that to look into the Git database and pull out the previous source code. And then at the end, it has a file name. So we can use the file name to just read the file from the file system and let us come up with some cool way to compare the two things. So we're going to pipe the output of that into our little compare.js script. This is how we're going to build a better Git diff. First thing we'll do, we'll read those lines in. We'll basically create an array for each line of difference, for each file that is changed, we'll get all of this information. And then we're going to split that up. We're going to split it up on each space, and then we'll grab the pieces that we care about. It happens to be like the last one and the second to last one or whatever. That'll give us an array of arrays. So now we're getting into this weird land where we're going to have tons of arrays of information. I think you could call this a tuple. I don't know about these things, but it's sort of like a tuple. It's like useful pieces of information stuck together in a little data structure like that. So here we have the file name of the change file, and then we have the MD5 hash of what that file was previously. Now, just a little refresher. If we want to parse the code, we use this Espree.parse function. And you'll see that here. So we're going to map over that array that we have. First thing we'll do, we'll grab the new version of the file. That's easy. Read file out of the file system. That was a piece of cake. The second one was a little bit trickier. We needed to use the exec_sync function of node to run a shell command, and then we'll call get show on the hash of that original file, and that will actually give us the full contents of the file. Then we'll return an object here that's parsed the old version and the new version. It looks something like this. So now we get this array of interesting information. We've gone from a raw get diff command to now actually having a data structure with the before tree and the after tree. Now, we're going to figure out now how to like take apart those trees and understand what changed between them. But I'm pretty impressed, like all the stuff that we did actually fits on one slide, plus or minus actual real life error handling, but you know, forget that slide. So you can do all that stuff right here. You can read from Git, you can read from the file system. You can create this object that contains the tree for the before and then the tree for after. So you see that the only change here is, you know, just at the bottom, right? Console log UtahJS and then console error some other conf. Once it's in a tree form, we have all this extra data to understand that actually not very much has changed. Of the meaning of the program, very little has changed. The program is basically the same. We just changed the inputs a little bit and a method name. Now, there's a couple different ways we could think about diffing those trees or trying to understand what changed. The first thing that came to mind, which is actually not the correct path, was using something like deep equal. Turns out that the tree, remember, it's just a JavaScript object. And if you have two JavaScript objects and you want to compare them, you could just put them into a deep equal command, you know, like Lodash has one of these, and say, hey, are you equal or not? And then if they're not, maybe do a little bit of analysis. So I started with that. I put together this deep equal command. You don't need to worry about the details. The main thing is, if it says if it's comparing two objects, it will go through each key in that object and recursively look down and compare for differences. That's not too complicated, you know. This is like an interview question at PayPal. By the way, we're hiring, but. So then I made a few modifications to this. I said, you know, we check the equality. If it is equal, then let's return that. And then if it's not equal, let's log that. And just with these two modifications of the basic deep equal function, we're able to get a more interesting variation on getDiff. We're not all the way to where we need to be, but we're starting to get a sense of something more interesting. Now our getDiff says, hey, this is what actually changed. We went from a log to an error. That method changed. It's an identifier as part of a member expression and part of a call expression. So it might be better than this if you know a lot about trees. You basically have something that says all of your things are the same except for those two little things change at the bottom. We're starting to use the trees to build a more valuable diff. But the problem is I can't keep a tree like, I can understand this tree just fine, but I can't keep a tree like this in my head, right? This is a program with 30, this is what the tree looks like for a program with 30 lines of code. It's not even a very big program. Like most of the components we have at PayPal are probably 100 lines of code, and we have thousands of them. So this is not really a good scalable method of trying to do some smart diffing. Instead, I want to talk about something a little more complicated pieces of code. Recently, to explain what I have up here, my family moved to Washington State. We were living in San Jose. Previously, like you said, we were living in Springville. It's all good. Moving is not super fun, but we have this idea of building a house. And building a house is this great vision. We bought this lot on this beautiful island in the Puget Sound, and the land is more or less cleared, and we thought that we just kind of give the builder some plans. We tell them what color the house should be, and you know, we figure just kind of like this code here. They would build the foundation, clear the lot, build the walls, the roof, sort of put all the house together and return it to us, and we get our house. This is the function that describes my life for the last 6 months. But it turns out that building a house doesn't actually work that way, especially when you're living on a beautiful island in the Puget Sound, because you have to get permits. And permits take a long time because trees. And bald eagles and all the beautiful things that live out there, you have to wait. So all of a sudden, my function that I was exporting has now become a callback function. I don't just get the house. I don't just show up with the things I need and I don't get house. I now have to wait, right? It went from being synchronous to asynchronous. Now this is interesting. I shoved these two functions into Git, and it's not particularly helpful. It basically thinks that I got rid of my function, replaced it with another function called getPermits, and then added another build house function. And that's with the -w flag that disables white space. With the white space showing, it looks like, Linus Torvalds just vomited all over my screen or whatever. So Git's not super helpful when it comes to complicated JavaScript code. And I know like GitHub is great, and you can use their diff tool to do some great code reviews. But I thought it might be interesting if we could try and figure out what actually matters when I'm comparing an old and new version of the JavaScript. What is like the essence of what I need to know? So in my head, just thinking about this, and again, this is just an example. This is not a real program. Like, you shouldn't really care about this get diff thing. All you should be thinking of right now is, I want to build something cooler so I can give this talk next year instead of Jamund. So here's what I actually wanted to do. I wanted to tell me that the exported function, I'm using ES6 module syntax in case you didn't notice, output from being a return to a callback. I want to know that it's now a callback function. That's actually the most important thing. The most breaking API change there was that it went from being synchronous to asynchronous. And then I'd also like to know that a new function was added. I don't need to see all the details of the function. I really just want to get the gist of what changed. And we can actually do that using the trees. We have this array of trees now, remembering that object we built before. Think of it like a forest, an array of trees. And we're able to use the tools we talked about, that visitor pattern. We're going to use a tool called ESRecurse. ESRecurse will let me say, let's look at the things we care about in these trees. We'll apply this to the old version and the new version. We'll sort of build an object that contains the key essence of those functions, and then we'll compare those at the end and figure out how to build a readable string. And we'll do it in like 4 minutes, because that's how much time we have left. So the first thing we're gonna do is call ESRecurse. And you'll see this. This is, again, the same visitor pattern that the Babel plugins use, the ESLint plugins use. It's something that you'll get very familiar with quickly. And in this case, we care about function declarations and export named declarations. That's fancy ES6 module terminology for just like your export a name function. So we're gonna call the same function on both of those types of nodes to figure out what's important with them. So here's how we're going to expect those things. First thing we're going to do is grab the name out of the node, because we care about the name. We're going to use the name to match and say, was this function changed, or is this a new function? Now, if you change the name of your function, my fancy program won't be able to help you there. So just don't change function names. It's very naughty. The next thing we're going to do is grab the parameters. It's really important to understand if the parameters of the function that you have created changed. You really want to know that. I want to know that the inputs and outputs have stayed the same or changed. That's basically how I'm going to tell if it's a breaking API change or not. So we'll use map to loop over the parameters API and grab out the names to give us a little array of the parameters. And then we're going to tell if the visibility is private or if the function has been exported. That's just, if I'm exporting it like an ES6 module, then we'll flag it as exported. Otherwise, it will be called private. And then in order to figure out, is this a callback function, or is this just returning something, we have this cool little function. So all I'm really going to do here is say, if the last parameter is a callback, then it's probably a callback function. If not, then you've got some messy code. If there's a return statement in the immediate body, so we're going to look for the return statement node in the body. If any of the items in the body of the function are a return statement, then we'll decide it might be a return. But if it's a callback, then the callback will take priority because you can return a callback, and it's still considered a callback. So with that, we get the essence of the function. In this case, we have a getPermits function. Its visibility is private. And we know that the only parameter of it is a callback. So therefore, we say its output type is callback. We're going to grab the essence of all of the functions in the file. And we're going to create this data structure, a more complex representation that has the file name, the function names, and then before and after essences of those functions. So I know you're all following along perfectly because reading code at conferences is the best. But if not, if you do want to learn more about this stuff, I have this posted all on GitHub, and you can go into my Twitter page where I've already linked to the slides and everything like that. So now that I have this data structure, I have all the information that I need to generate my nice and simple diff. The next thing that I'm going to use is reduce. How many of you are very familiar with the reduce function on arrays? Okay, about like half. I would really say that in the last couple of months I've used it and I found it can do really powerful things. I think oftentimes I think, oh, that's fancy stuff. I don't need to get into that. I can use map and filter all day long, but reduce is fancy. No, reduce is cool. It's really powerful. Here I'm going to reduce that big object down to a string, or sorry, reduce an array of objects down to a string. It's pretty neat. You'll see here that I'm passing into reduce two methods. I'm passing in the function that it iterates over, and then I'm also passing in a string, an empty string. That empty string becomes the start thing, which I typoed there. I was going to say output. You might call it accumulator or previous, whatever you want to call it. And then we're going to add to that output every single time. So here, the first thing I'm going to do is say, I'm looping over each of those functions in my data structure. So if you go back, I'm looping here over the build house function. And I'm going to call get what happened on build house. Now here's the cool thing. Because I've built this great data structure, my get what happened, turning that from data to something human readable is really easy. All you have to do is say, if we have a function.before, then something was added. If we have one now, but it didn't exist before, it was added. Sorry, if we had one before, but we don't have it now, then it's been removed. So again, we're taking information about the data and we're just turning that into a string. And then finally, we're going to compare output types. And we'll say, if the output type's changed, if it's gone from a callback to a return, we'll return a string that explains that. We've now taken that big object, using reduce, converted it into just this little string. The exact string that we wanted. The exported function went from being returned to a callback. The private function was added. And then all we need to do is use map over that array of strings, join that with just a new line, and we get this happy ending. A human readable diff output. It's very simple, more or less. So there it is. We've done something interesting with trees. I hope I've gotten you excited a little bit about what's possible with them. This isn't particularly, this may or may not be an interesting example to you, but just think about all the interesting things you could build if you had robots to build your code for you. Remember, these trees are super powerful. You can use them for code transformation, for migrating your code from one way to another, or just inspecting it by writing custom rules for things like ESLint. I hope today you got a sense of what you can do with them. Thank you so much for listening.